Hello everyone. In this video, we're going to talk about heap sort using C++ priority queue. If you ever wonder how priority queues work internally, this video is for you. And so we'll start from the basic idea of max heap and min heap and move on to the multi-condition priority queues. And finally, we'll solve a fun and practical problem using priority queues. So let's get started. First things first, when it comes to max heap, which is default in the Visual Studio, if we heap sort this data, it will become a descending order. On the other hand, when it comes to min heap, which uses the greater operation in this case, if we sort out this data, it will become an ascending order. So let's move on to our first example. Let's say we insert these numbers randomly, and as you can see, those are the max heap and min heap rule based on the binary heap tree, which I'm going to show you later. So I'm going to show you how max heap and min heap works in the Visual Studio. First things first, we're gonna write down the basic code first. We have to include the queue library and the priority queue integer type. It's gonna be max heap, which is our descending order. I'm gonna name it DSC. Well, this is gonna be a min heap, which is our ascending order. But in this case, we have to throw in more parameters. Like I said before, it will be a greater integer type. There we go. Well, when it comes to max heap, it would become less integer type. But in this case, this is the default already, so I'm gonna erase it for the convenience. And I'm gonna push the random numbers 4, 1, 7, 25, 2, 354, and 46. There we go. And then I'm gonna hit sort. Well, before you do that, I'm gonna check the monitor. Well, as you can see, you might a little bit confused with the order of the data, or when it comes to min heap, you might confuse with this order as well. But if you just draw the heap tree, binary heap tree based on this order, you can probably notice that this is the right order for the descending order or the ascending order. And so if I continue to do the heap sort, we use the while loop until this priority queue got empty. We use the top and pop it to remove the data. And then if I execute this file, as you probably can tell, this is the descending order, which is max heap, which is our default in Visual Studio. And this is the ascending order, which is min heap. There we go. Well, let's move on to our next example. So imagine an emergency room. So the patients arrive at different times, have different ages, and different levels of urgency. So our priority rules are like this. The top priority would be the level of urgency, and if they have the same level of urgency, uh, you know, we have to consider the arrival time based on the first come first serve. And the last priority, if they have the same level of urgency and they arrive at the same time, we have to consider the age. The older people must be served first. And so in this case, we need to overload the comparison operator. So in this implementation, since we're using an operator like this, and we're going to use the priority queue with the default version in Visual Studio, which is the max heap. We deliberately designed the comparison so that the right-hand parameter has higher priority. So this is a design choice based on my preference. So it's not a language rule, just so you know. Well, I'm gonna write down the basic code first. Well, first things first, we need the priority queue with the node type. And so I'm gonna push the random numbers first. The order would be urgency, the level of urgency, and the arrival time, and the age. So urgency, arrival time, age. There you go. 8, 12, 40. Just throw in the random numbers. There we go. And then before we do that, I'm gonna write down the project name, which is emergency room treatment order. I'm gonna overload the comparison operator. This is the comparison operator, so you know. And so, well, I intentionally reverse the order of this parameter. A should be, which is the right parameter in this case, has the higher priority all the time. And so if level of the urgency, the A's level of the urgency is higher than B's one, I'm gonna return true. If it's the opposite situation, I'm gonna return false. And if the level of the urgency are the same, we have to consider the arrival time. If A arrive earlier than B, I'm gonna return true. If this is the opposite situation, I'm gonna return false. And if the level of the urgency are the same, and if they both patients arrive at the same time, we have to consider the age. If the age of A is older than B's one, I'm gonna return true. Otherwise, I'm gonna return false. There we go. And this is how we overload the comparison operator. and I need a while loop. We need to pop. And this is how we read one node in this case. Level of urgency. And the arrival time. And the age. There we go. So if I execute this file, as you probably can tell, the output clearly shows that urgency comes first, followed by arrival time and then age. Well, patients with urgency 8 are handled before urgency 5, and earlier arrives are prioritized, as you can see. And the age is used only as a final tiebreaker. So there we go. Let's move on to our last example for today. It's called the magic stone fusion system. So each magic stone has an energy value. In this test case, it would be 4, 8, 6, 12, and 15. It must be random numbers. And so you must always combine the two weakest stone, which is our rule number 2. And cost of fusion is the sum of energy values, which is rule number 3. And so the total cost should be minimized as well. So for this example, I'm gonna take out 4 and 6 first, and 10 would be the cost of fusion, and the 10, the stone of 10 is created, and 4 and 6 is removed, and we're gonna take out one more, 10 and 8. There we go. 8 and 10. The cost of fusion would be 18, and so the new stone will be created to 18, and the weakest stone would be 12 and 15. So the cost of fusion would be 27. The new stone is created 27, and for the last iteration it would be 18 and 27. The cost of fusion would be 45. So if I add entire costs, I forgot this part. The last stone would be 45. There we go. And so the cost of fusion, the total number would be 3, 4, 6, 10. So it would be 100. And the last stone in this area would be 45. So we're gonna print out the cost of fusion, the total cost of fusion, and the energy value of the last stone. So we're gonna repeat the while loop until the queue size becomes 1. There we go. Well, just write down the basic code first. Well, in this example, I was supposed to use the bool operator overloading version, but still we can use the priority queue with the min hip version, because we all the time pick up the weakest stone from the priority queue all the time. So this is the perfect example for the min hip, and I'm gonna show you this first. 4, 6, 8, 12, 15. We need the total cost. I'm gonna repeat this process until the queue, the priority queue size becomes 1. And we'll need the 2 stone. And I'm gonna make the new stone. And I'm gonna sum up to the total cost with the value of the new stone, and I'm gonna push the new stone to the priority queue. Yeah, and then I'm gonna print out the total cost. I'm gonna print out the last stone energy value. There we go. Yeah, it's 145. There we go. And then I'm gonna show you how to use the, the comparison operator overloading version. Operator. All the time we use this, we need the structure. We're gonna pick up the weakest value of the stone. Since we have the single value, which is integer type, we cannot make the priority queue with the integer type. This is the rule. There we go. Yeah, the result of this code is exactly the same to the previous one. Well, as you probably can tell, technically this is a classic greedy algorithm problem. So by always merging two smallest stones all the time, so we minimize the total fusion costs here. Anyway, this is all about today's video, and I hope you find it very useful through this video. Thanks for watching. See you on my next video. Bye guys.